All right, so in chapter 3, there's an example of induction. Right after problem 66, it starts kind of talking about induction and how this all works. Example 12, I just kind of wanted to go over that a little bit and how this works. So with induction, I sort of consider this to be into 3 separate steps. There's a basis step. So basis step. There's going to be an inductive step. Inductive step. I'm going to leave some space in here, and then at the very end we can write down the conclusion. So 3 different kind of things, of which the inductive step is kind of the major amount of work on these proofs. So the basis step is just our base, and a lot of times we're going to either choose 0 or choose 1. So because this equation starts with a 1, we're going to use 1. So for n equals 1 in this equation, if I look at the left-hand side and look just at 1, and then the right-hand side I'm going to plug in 1, so 1 should equal 1. Times 1 plus 1 all over 2. 1 plus 1 is 2. 2 divided by 2. Yep, that is 1. And there's our basis step. We've shown that this works if n equals 1. Now the inductive step, we are going to assume that this works in the for the kth step. So I'm going to write this as S of k. So if it works when we have k, if we assume that, and we want to show in the inductive step that it works for k plus 1. So it works for the next one. If we reach k, then we can go one more and we can reach to k plus 1 with whatever we're trying to prove. So if we assume that k works, so what we're going to do on this inductive step is first we're going to assume that what we were trying to prove works when we hit the kth number. So instead of n, we're going to have the kth number. So we're going to assume that 1 plus 2 plus, etc., adding up all these numbers, adding up all the way until we hit k, that is going to equal k times k plus 1 all over 2. And what we want to do is to show that this works if we ended instead of k at a k plus 1. Now we're going to use this step we just did. Because we wanted to add a k, we wanted to stop at k plus 1, I'm going to add k plus 1 to both sides. So 1 plus 2 plus, there's that k, but now I'm going to add k plus 1 to this side, the left-hand side. And I'm going to add k plus 1 to the right-hand side. And what I want to do is to show that if we have k plus 1, that it's going to work right in this formula in here. So that instead of n right there, it would be k plus 1. Instead of n right there, it would be k plus 1. And then we'd be adding 1 to that. All right, I can't make that arrow go away. Oh well. All right, so I want to show that on that right-hand side. So the left-hand side is going to stay the same, but I want to do some work to that right-hand side. So left-hand side is going to stay the same here. Then on the right-hand side, let's find a common denominator, first of all. So that would be 2. So I'd have k times k plus 1 plus 2 times k plus 1, and that's because I'm making a common denominator over this entire thing of 2. Now on this right-hand side, notice I have k plus 1 in both of those terms, so I can factor out k plus 1. What's left in the first term is a k, what's left in the second term is a 2, and this is all divided by 2. So if you notice back up to what we were trying to do to begin with, right in here with this arrow, oh, there's another arrow, great. let me pause. Okay, I figured out my arrows on this screen. All right, so what I wanted to show in all of this is that we assumed S of k, so we plugged k in there, we plugged k in all of there. We did some algebra down to this spot, and now instead of n up here, we have k plus 1. So what we've done is jumped from a previous number to a next number. We've jumped from k to k plus 1, and that is the inductive step. If we can show that if it works for every k, it will then work for the next one, the k plus 1th term, so it looks exactly like this right-hand side, but with k plus 1, then we are done. We have shown that this works. And we can now state our conclusion that 1 plus 2 plus, all the way until we hit n, no matter what number that is going to equal n times n plus 1 all over 2. So once again, on the to do a proof by induction, there are kind of 3 main steps in here. The first one is a basis step. This step is either going to be n equals 0 or n equals 1 or whatever n we are starting with, and you just want to show that it works for the first one. This is like climbing the first rung on a ladder. This next step says that if we reach somewhere in the middle of the ladder, well, we'll be able to go one more rung on the ladder. A lot of times there's just algebra involved in showing that, so you can assume for k, and you want to show it works for k plus 1. And then once you've done that, you can just state your conclusion at the end. So now it's time for you guys to do another example. So on example for problem number 67, you are going to show that the sum of squares of the first n positive integers is n times n plus 1 times 2n plus 1 over 6. Now I wanted to get you a little started on this because the sum of the squares of the first positive integers, so sum of the squares is 1 squared plus 2 squared, which is 4, plus 3 squared, which is 9, plus 4 squared, which is 16, etc., etc., etc. We will end at some square. And you want to show that that is equal to n times n plus 1 times 2n plus 1 all over 6. So once again, you'll have a basis step, probably n equals 1 because we have 1 right here. Then you're going to assume this equation is true when you have k instead of n, and then you're going to show that this equation is true when you have k plus 1 all plugged into it. All right.